Okay, we are recording. So, yeah, any questions on yesterday's moderately bad lecture? I'm sorry. Um, yeah, anybody wants me to fix something in there or to clarify something? No. Okay. Um, okay, so then let's move on to planar graphs. Some motivation. So I'm not telling you what they are, but you'll see very soon what these are. Uh, motivation for planar graphs. Actually, the origin of the study of planar graphs is very old. Um, they're fun, actually. I mentioned this question about maps from the late 19th century. But there's some serious reasons why you want to study planar graphs also. For example, if you're going to design circuits, you might have to understand if the graphs you're designing are planar or not, because you can't have wires going on over another. Um, road networks and such. And surprisingly, I mean, this looks a little bit like, yeah, just like it seems like I'm trying to sell something, but um, planar graphs are a remarkable family of graphs that have generated a lot of very, very beautiful theory and graph theory that goes way beyond planar graphs. But that's also way beyond what we're doing here. So let's just start with a little puzzle that you may have seen before. It's a well-known puzzle. And it is the following. And it'll illustrate what a planar graph is or isn't. So we have three houses and three utilities. By utilities, you think electricity and water and such. And you have to connect all three houses to all three utilities without any crossings. So we have a situation like this. We have a house, we have another house, we have another house like that, and we have three utilities like that, and we'd like to connect these utilities to the houses like this without any crossings. Okay, so maybe I can go here, maybe I can go here, maybe I can go here. Now I'm good for this one. Now I can do this one, and I'm in trouble now, right? So you might mess around with this puzzle for a little while and see that you're going to have a lot of difficulty doing this, and in fact, it is not possible. Um, so this sort of illustrates the idea behind planar graphs. So let's define these properly, okay? So I'm going to, I'm sort of following what's in the book, but I don't remember. I mean, I have my own notes and I've made modifications because I didn't like the way they did it in the book in certain places. So if you're reading the book, you will see differences, but it all comes down to the same thing. A planar representation, let's start with that. So a planar representation of a graph. So what is that? So let's say my graph is G with vertices V and edges E. What is a planar representation? I have vertices and I have edges. I'm going to represent them in the plane. So it's a set of points and curves in the plane. Okay, R2, where points, this is going to be sort of, I'm not going to do this very formally here, because otherwise it would take us like half an hour and it would be a waste of time. Okay, so I'm going to be very informal and you will understand immediately what I'm talking about. So where points represent vertices, represent just like the pictures we were doing of graphs up to this point, and curves connect uh, points corresponding to adjacent vertices. Okay. Let us admit someone else. Yeah. Okay. Um, so points represent vertices, curves connect points which are adjacent vertices in such a way, and that's the so that's a representation in the plane of our graph. But if I call it a planar representation, it means that these curves do not cross, such that curves do not cross. So they're allowed to intersect at the points where they meet, but not anywhere else. Okay. And what is a planar graph? A planar graph is a graph which admits at least one planar representation. Okay. So a graph is said to be planar if it has at least, if it has a planar representation. Now, at this point, it is not clear whether all graphs are planar or none are, but it's clearly, I mean, if you think about it, it's clearly there are planar graphs. It's not so obvious that there are graphs which are not planar. This is much harder actually to figure out. So here's some illustrations of this. So you remember these basic graphs that we saw, the complete graphs. Let's take a bigger one, K4. K4 is in fact planar. So K4 is planar. So to show that a graph is planar, all I have to do is provide one planar representation and that's it, right? So that would be the easy thing to do. To show that a graph is not planar, that's much harder because I have to show that there is absolutely no way to represent it in the plane. So that's intuitively much harder, and that's the case. So K4 is planar. What is K4? 4 vertices, all possible edges. So let's see if we can do that. Let's try that, like that. That's a planar representation of K4, right? So there are no crossings whatsoever. Or another possibility, so there are many possibilities, is like this. That's also a planar representation of K4, okay? What about, let's say Q3? You remember Q3, what is that? That's the hypercube of dimension 3. Let me draw it in a non-planar way. So this is just so that you see what this, so this is not a planar representation, right? There's a crossing, there's actually 2 crossings, but you can modify this. Okay, so this is not planar, but the following is. So draw it this way. So you put the little square here, the little square outside, the big square outside, and like that. That's a planar representation, right? There's no crossings of any curves. Now, a question that you might ask yourself is say, okay, well, with 2 examples, that's a stretch, but it turns out that there's a not so obvious theorem that says that if you have a graph which is planar, so if it has a planar representation and it's a simple graph, then there is a representation that uses only line segments. It is possible, as you see in these 2 examples, I I can do it with, I could do it in those two examples with only line segment, no, nothing curved, if you wish. And that's true in general, okay? But we're not going to use that. And I'm not going to prove that either. Okay. Before I move on to non-planar graphs, I want to make a couple of observations. So two of which are easy and not interesting. But I mean, at some point you might ask yourself, so here's some observations. Okay, so in what follows, I am going to assume the graphs I'm looking at are simple graphs. Remember, that means that there's no orientations on the edges. Obviously, this has no impact on whether something is planar or not, right? If there's an orientation. Um, and loops. I'm assuming there's no loops, okay? But if you think a little bit about this, the loops don't make any difference, right? You can always add loops and you're not gonna mess up the planarity of a graph. I mean, you just think about it a little bit and you'll see. So in what follows, we will consider only simple graphs, right? So undirected and no loops, but it's not difficult to extend all the results to graphs with loops, and in fact to multigraphs, right? So having multiple edges is not going to make any big difference in the whole analysis that we're making. If you think about it, right? If you have a planar representation of a graph, if you have an edge like that, you could have several edges. You don't need to make any crossings to allow these new edges. So, and loops is the same thing, right? So to simplify everything, we're just not going to consider loops anywhere, okay? The second observation is actually a much more important observation. It is not as obvious. Here's another one. So I'm talking about planar representations. I could also choose to represent my graph, let's say, on a sphere. Okay, so spherical representation. So same as planar, but on a sphere. Okay, so fact, and this is really a very useful fact. And if you don't see it right now, what I'm going to state, think about it a little bit by yourselves, but try really to reach the point where you say, okay, yeah, this is true. This has to be true, because it's really, really very useful. Okay, so a graph has a spherical representation if and only if it is planar. So to represent a graph, to draw a graph on a sphere, or to draw a graph in the plane with no crossings, there's no difference. Okay, and I'm going to try to convince you of this. Okay, so why is this? Okay, let's start with planar to spherical. Hopefully that should be the easiest one. Okay, so if G is planar. Okay, let me just do a little picture. So let's say we have G like this, and it is planar. So it has a representation, maybe with curves, it doesn't matter, right? So maybe it looks like that. So maybe this is G in the plane, okay? do you see that I mean, the sphere you're using can be as big as you want, right? So does everybody see that you can draw this on a sphere? If you just take a really, really big sphere, right, you can just draw this on one little part of the sphere and you're done, right? Everybody sees this, yes?
Makes sense to me.
Yep.
Yep.
Yes, good. Okay, so you just draw it. So let's say, let's try that with a different color. So let's say this, like that, you draw it on a sphere like that, right? So obviously can be represented on a big sphere, right? So if you just take a really big sphere, you just draw the graph on a little part, you know, just like people who think the Earth is a sphere. No, it's flat. So okay, so now suppose you've drawn, so now maybe the less intuitive direction is the other one, because you say, well, now I can sort of wrap things around like that, right? Okay, so now let's say that G, let's say now G has a spherical representation. Okay, so this is one direction, that's this direction, and this is the other direction. So now I want to go from a graph that has a spherical representation and show that it is planar. Okay, so the sort of tricky part is if it, right, you see that this thing is wrapping around, like, you know, think of, so think of, let's say, a tetrahedron, for example. That would be, you know, you could draw a tetrahedron on a sphere like that, right? So this, you see that the arc on, which is dotted line, is on the other side of the sphere, okay? So you say, wait, okay, so how do you make that planar? Well, the trick is this, is you see in my previous picture, if the graph is like on a small part of the sphere, I'm good, right? I can just cut around and I can just put it on the plane like that. So that's the only tricky part, is how do I go from a graph that would be like around the sphere? How do I go from that to a graph that's only on a part of the sphere? And what you do is just think of it this way, like you puncture the sphere inside one of these faces, right? So let's say, so you pierce, if you want, so imagine that you puncture the sphere in a face of the representation and open up that face. I don't know if you can see what I'm saying. So if you take the tetrahedron like that and you put a hole inside one of these faces and you open it up, right? So what is going to happen is you're going to transform this. My color coding is not consistent, but anyway, so what you can do is you've got this like that, and you can take this thing back all on one side of the sphere. Does that make sense? Can you visualize this? Some people have difficulty visualizing this, but let's say you have like a face on the other side of the sphere. You can just bring everything like this to one side of the sphere, on one half of the sphere. Does that make sense? Can you see this?
Yep.
Yeah. Okay. So in other words, you just shove the graph on one hemisphere. Maybe that's a better way of saying it. So you can pull out a face to put everything in one half of the sphere, right? I think this is better. So by expanding one face. Okay, it's hard to do this in 2 dimensions, strangely enough, because we're actually talking about things which are 2-dimensional. But again, if you have a spherical representation, think of let's say a face at the bottom like that, and just pull it up until that becomes it's on the equator. So all the graph will be on the top part of the sphere, right? And you can just flatten out in the plane. Okay. So try to convince, if you don't see it now, just try to convince yourselves that this actually works, because I'm going to be using this trick to simplify some arguments. Okay. So so we've seen some planar graphs. I think everybody understands what the concept is. It's actually pretty simple to define. They're not so easy to play with, as I'm going to explain right now. So I'm going to do a proof, which is it's solving this puzzle. Okay, so here's a fact. This is not a proof that I like very much, because it uses atomic weapons to kill an ant. Okay, there are much simpler ways of showing this, but here, I mean, it's going to show you in a sense how difficult this can be if you don't approach the problem the right way. So here's a fact. It's that K33 is not planar. Okay, so this basically is solve the puzzle above, right? Because what is K33? If you remember, K33 is the complete bipartite graph with 3 vertices in each color class. So what is K33? It is the following graph. So you have 2 colors, right? And everybody in each color is connected to everybody else. So let's call these, I'm going to give names to these vertices 1, 2, 3, 4, 5, and 6. So these are all connected like that. These are all connected like that. These are all connected like this. Okay, now again, I mean, maybe this is obvious, but just to make sure, a graph is planar if it has at least one planar representation. The fact that this is not a planar representation does not prove that K33 is not planar. Maybe there is another way to draw it, right? So this is clearly not the right way if it is planar, but it doesn't mean that it is not planar just because there's a non-planar way of doing it, right? So we have to show that there is no way to do it with a planar representation. Okay, so here is the proof, which is not the best proof, but anyway. Okay, it'll convince you. At least it'll convince you. So suppose it's a proof by contradiction. So suppose there exists a planar representation. Okay, so look at the vertices 1, 4, 2, and 5. Okay, so we're going to practice a little bit what we saw last time. If you look at those 4 vertices, they induce an induced subgraph, right? A subgraph, which is a 4 cycle, right? So if you just look at those 4 vertices, you erase all the others, and you just keep those edges between some of them, those that exist, right? You will see that. So 1, 2, 4, 5 induces a 4 cycle, right? So in any planar representation, you must have this 4 cycle. So in any planar representation, we have this cycle. Okay, so this is forced. We're going to have something that looks like this. Maybe we have very complicated curves, but certainly we have something that looks like that in our planar representation. So I'll write it this way. This is 1, 4, 2, 5. Okay, so somewhere in our picture of this graph in the plane, there must be a curve from 1 to 4, a curve from 4 to 2, a curve from 2 to 5, and a curve from 5 to 1. Okay, for sure. Now here is the atomic weapons being used. It is the Jordan curve theorem, okay, which I'm not really going to state here, but this is the ratio to how simple it sounds and how hard it is to prove is maybe one of the worst of all theorems. So the Jordan curve theorem basically says that if you have a closed curve in the plane, it divides the plane into 2 different pieces. That's what the Jordan curve theorem says. Okay, but this is a very difficult theorem to prove. Okay, surprisingly. So using the Jordan curve theorem, the cycle divides the plane in 2 disjoint pieces. Call them region 1 and region 2. Okay, so I have region 2 on one side and I have region 1 on the other side. Now, again, my picture, and this is one of the reasons I don't like this proof, is that you have to be really careful about assumptions that you're making, because we're saying, so we have some curves that connect 1 and 4, some curves. It could be really very complicated looking, but we're drawing it as a very simple little thing, right? But certainly the Jordan curve theorem applies here, and we're going to split the plane into 2 pieces. Okay, that's for sure. Okay, so now look at the vertex 3. It has to be in R1 or in R2, right? So vertex 3 is in R1 or R2. Let's consider that it is in R2. Now you're going to say, oh, but wait, they're not the same. R1 is like this big infinite region, and R2 is this finite region. And this is where spherical representations are so cool, because if you draw this on a sphere, there are no infinite regions. You're going to have 2 finite regions, right? And so the argument that I'm going to make for R2 would be the same for R1. Okay, so without loss. And if you don't like this, if you don't believe me, or you don't want to believe me, good for you. I'm not saying I'm lying, but you have a good reflex. Then if you don't like that, then try to do the argument for R1. It'll work out, okay? But without loss of generality, use a spherical representation. So by using a spherical representation, everything is the same, whether because being inside that curve or outside, it's the same thing, right? Because it depends just on how you look at it. But in the plane, there is a difference. There is a finite piece, R2, and there's an infinite piece, R1, which is annoying, okay? So, but I'm saying that it doesn't make any difference whether you argue whether the vertex is in R2 or R1, because you can look at this on a sphere, okay? So without loss of generality, 3 is in R2. Okay, so here's how this thing looks. Nope. Yes. Okay, so now 3 is somewhere here. Okay. Let's go back to our graph here. What is 3 connected to? It is connected to 4, 5, and 6. Okay, so 3 is connected to 4, 5, and 6. So it means that I have a curve going from here to here, and I have a curve going from here to here. Okay, so you mean that both R1 and R2 become finite? Yes, exactly. Yes. Yeah. So I mean, you can visualize this. Let's say R2 is like really small, right? And R1 is infinite. But if you draw this on a sphere, you can just shift things around so that R2 or R1 becomes small, right? You can just, if you understood the argument of what I did when I went from sphere to plane, you can shift things around so that big faces become small faces. It makes no difference on a sphere. Yes, that's the trick. Okay, so when you argue on a sphere, you don't have to worry about which side you're in. They're all the same. Okay. So 3 is inside, it's in R2, and it's connected to 4 and 5. So we have a situation like this. So I apply the Jordan curve theorem again. Okay, so Jordan curve theorem again. We have two disjoint regions, let's say A and B. So this would be A, this will be B, and R1 is outside. Okay. So I've got the vertices 1, 2, 3, 4, 5, and now 6 must be in either R1, A, or B. Okay, so vertex 6 is in R1 or A or B. Let's just copy our graph again to bring it over here. So, yep, let's make it a little smaller. Okay, so I'll need this too. Okay. All right. So vertex 6 is either in R1 or in A or in B. Suppose 6 is in R1, but 6 is adjacent to 3. That's bad, right? See, 3 is inside R2 and 6 would be in R1. I can't cross that closed. I'm going to have to cross somewhere, right? So we'll be forced to cross. Right? So if 6 is completely outside, then it's connected to 3. So I need a curve from 6 to 3. I'm screwed. Okay. So suppose now 6 is in, you can see it's going to be a similar argument in all the 3 cases. So suppose 6 is in A. The problem now will be that 6 is connected to 2. 6 adjacent to 2. That's also bad. Right? You see, if you're inside A, 2 is outside, you can't reach it without crossing. And if 6 is in B, then the problem is 1, right? 6 is connected, 6 is adjacent to 1. And that's bad. And so that's the proof that there is at least one graph which is not planar, and that's K33. Okay, there are others. But we're not going to do proofs like this one. There's a much easier way to, I mean, there's a more elegant way of doing it than this. Okay, is this, I think this is convincing as long as you believe the Jordan curve theorem. This I think is convincing. It's not the argument is not too difficult, but again, it uses like heavy artillery to do this, which is not so nice. Okay, but in any case, we do have at least one graph which is not planar. Now we'd like to develop some tools to show that other graphs are not planar, but don't require this kind of messing around. Okay, and one of the most this is really a very, very, very nice theorem. It's old. Euler's formula gives a condition on a planar graph on the number of vertices and number of edges that it has. And you can use it to show that some graphs are not planar just by elementary arithmetic. So it's very, very nice. The applications I'm going to do on Thursday. Okay. So our next result is Euler's formula. So this is a very well-known, beautiful result. Oh, that's beautiful too. Beautiful result about planar graphs. And in fact, it goes way, way beyond planar graphs, and it goes way, way beyond graph theory. It's the starting point of, I mean, I'll tell you a little bit about it in just a sec, but let's just at least state it. So when let's say you have G, a graph which is planar. So I have a planar representation of G. It divides the plane or the sphere, depending on how you want to see it, into faces. Right? So what's a face? It is these regions which are that's a tough one. Because I have to use this Jordan curve theorem in a sense. So these are the closed regions separated by the curves in the representation. Okay, so here's, I'll just illustrate it this way. This is not easy to define properly in a simple way. So this is K4, right? This is a planar representation of K4. You see that you have these faces. There's this face, this face, this face, and this outside face. There are 4 faces. And there is one which is the unbounded face, the outside one, right? So when you have a planar representation, you have these bounded faces and one unbounded face. If you do it on a sphere, there is no unbounded face. They're all equivalent, okay? So Euler's formula, what it does is it tells you there's a deep connection between the number of vertices, the number of edges, and the number of faces in the planar representation of a graph. So here is Euler's formula. And we're going to prove it because it's a very, very nice theorem, and it's not difficult to prove. Theorem, Euler's formula. So let G be a connected. So we need it to be connected. If it's not a connected graph, then you can still figure out a formula, but it introduces slight annoying things. So it's easier if G is connected. So let G be connected, be a connected planar graph with V vertices. So this is the number of vertices, we call that V. E edges, so that's the number of edges, we call that E. And F faces in a planar representation, right? So you can't talk about faces of a graph because you need a representation to talk about faces, right? But the number of faces will always be the same okay? And it is controlled by the following formula. So this is Euler's formula, then V minus E plus F is equal to 2. So this is Euler's formula. Okay, so I am going to so next class I'm going to use Euler's formula to prove some very, very nice extra conditions on planar graphs, and this will make it very easy to prove that certain graphs are not planar just by arithmetic. Let's see. So again, I'm assuming my graphs are simple graphs, no loops, no multiple edges, no orientation, no nothing. That'll make it easier. Okay. A little comment. So that number 2, which is there, looks weird, right? So it's just like, what's this 2? This is called the Euler characteristic of the sphere. The number 2. So this is a number that's attached to the sphere, Euler characteristic of the sphere. So surfaces have different characteristics. It depends on the number of holes in them. So a sphere has no holes, so its characteristic is 2. A torus, a donut, so the Euler characteristic of the torus, that's a donut, right? So like that is 0. I'm not telling you why that is, but you see what's going to happen, and that's really cool, is that if you take a graph and you draw it on a torus, right, and you have no crossings, then you will have vertices and edges and faces, and V minus E plus F will be equal to 0. Okay, so, and on a torus, if you have a representation, a toroidal representation, you'll get V minus E plus F equals to 0. And there are graphs that you can represent on a torus that you can't represent on a sphere. For example, K7, you can draw it on a torus. So here's an example here. I'm not going to give this as an exercise because that's sort of not so easy. K7. Oh, K7 is not planar. There's no way to draw K7 on a sphere without any crossings, but you can do it on a torus. That hole helps you actually do that, okay? And if you do that, you count the vertices, the edges, and the faces, you will get that V minus E plus F equals to 0. If you have 2 holes, the characteristic is -2. And the more holes you add, and you can represent more and more graphs on these surfaces. And there's a whole theory behind this, and it's huge, and we're not going to go there. Okay, so there's a big fat etc. here. Okay. All right, so let's go now to, so we want to prove Euler's formula. I'm trying to remember if you saw Euler in Cal 1 or Cal 2. I mean, not that he was actually sitting in your class, but if you saw any math by Euler in, I'm not sure. So he's a Swiss mathematician, one of the great mathematicians. Second most famous person to come from the city of Basel. First one, anybody can name the most famous person from Basel, Switzerland? I'm disappointed.
Federer?
Roger Federer is from Basel. Okay. I'm just this is tea. Yes, it's not whiskey. Okay, so we want to prove Euler's formula. We'd like to prove that whenever you take a connected simple graph and you represent it in the plane or in the sphere, you count the number of vertices, edges, and faces, you're going to get always. Not yet, yes. Yeah, it's a bit early for me. Not there yet. Okay. So to prove Euler's formula, we're going to use induction. Okay. And but I'll need some extra stuff. It is 5 p.m. somewhere. Yes, indeed, but not in my stomach. Where was I? Yeah, so I need trees. So I need to prove the result for trees in my induction somewhere. And I talked about trees last time. So just to refresh your memory, what is a tree? So a tree is a connected graph that contains no circuit. So it has no induced subgraph, which is a cycle, right? So I drew some trees earlier, right? This is a typical tree. So there are no cycles, no circuits inside, okay? But it is connected, okay? So you might guess that trees are planar, right? Looking just at this picture like that, if you intuitively, if you can draw something that looks like that, you can draw it in the plane with no crossings. So they should satisfy Euler's. Okay, let's do it this way. Okay, so intuitively, and but I don't need the fact that trees are planar. I won't need this. So intuitively, trees are planar, and so should satisfy Euler's formula, right? So if Euler's formula is true, it would have to be true for trees. Let's see what this means. Okay, so look at that picture there. How many faces does this planar representation have?
Only has one face.
Yeah, so it's just that infinite face. There's no, obviously, because there's no circuits, you can't have any closed face. There's only one face, right? So notice a tree is acyclic. Right? Means only one face. So if it is planar, there is only one face, that's for sure. Now I'm supposed to have V minus E plus F equals to 2. And so V minus E plus 1 equals to 2. So V minus E equals to 1. So I'm going to get that E is equal to V minus 1 is forced. So if Euler's formula is true for trees, which it is, but I haven't proved it, then for sure, the number of edges in a tree should be always one less than the number of vertices. And that's what I'd like to prove. That I need this to for the rest of my proof. Okay, so we prove there. So again, I didn't prove this. I assumed that trees are planar, and if they are, this had better be true, and I'm going to prove this independently. Okay, so here's a lemma. So this in fact is true if G is a tree with V vertices, then it has v minus 1 edges. Okay, this is a classic important result about trees. These are, in fact, this actually describes exactly trees. These are exactly the graphs. Trees are exactly the graph of this strange property that they have exactly one less edge than vertices. Okay, just to illustrate, right? So the one element tree, it has one vertex, 0 edge, right? The one edge tree, so 2 vertices, 1 edge. What if we have 3? If we have 4, it could be this or it could be this, right? These are all trees, and you can see that it has, I mean, for small values, it's certainly true, right? So it's clearly true for small trees. Okay, but I want to show it in general. Okay, so I want to make sure this is true for any tree. So I'm going to use induction on the number of vertices. Yes, okay. So we use induction on the number of vertices. Okay. So let's say that v equals to 1, then this is obviously true. I've just observed it. Right? 1 vertex, no edges, 1 less. Okay, that's bingo. So now suppose that the result is true for any tree that has, let's say, k vertices, and I'm going to show it for all trees that have k plus 1 vertices. So suppose that the result is true for all trees with k vertices. We show it is true for all trees with k plus 1 vertices. Okay, so I take an arbitrary tree. So let G be an arbitrary tree with k plus 1 vertices to show it has k edges. Okay, and I want to use the fact that I know it's true for all trees with 1 less vertex. This is a classic type of argument using graphs. Okay, you see this in, do I have one in this paper? A paper I've been refereeing, maybe not, but yes, this is like absolutely standard and classic. So I want to use the fact that I know this is true for trees with k vertices. I have a tree with k plus 1 vertices. What I need to do is somehow get a tree with k vertices out of this one and, you know, jack up the result for the graph that I have. So let me just illustrate what I'm trying to do. Okay, so here is idea of what we want to do. Okay, so let's say I have a tree like that, and I don't know, this isn't G, okay, with k plus 1 vertices. I don't know how many edges it has. I mean, obviously I've drawn it, I can count it, but that's not the point. Think of this as the graph we don't know anything about. But I know that if I have a tree with 1 less vertex, I have the right number of edges that I want. So what do you do with this graph? You say, okay, look, if I take this guy out, just remove it, right? And the edge there. what remains is a tree with k vertices. It has the right number of edges, and this just count everything and it'll work out nicely, right? So notice that if we remove vertex x, we get a tree G prime with k vertices, and by induction hypothesis, k minus 1 edges, right? So this is, so G prime is this tree here, the blue tree. Right? So I've removed that vertex and the edge connecting G prime to that, right? So I count by induction hypothesis, I have the right number of edges. So you just add an edge and a vertex, so everything works out, right? Does everybody see the strategy? Does that make sense?
I mean, I see the strategy. I'm just not sure. You have to prove that you can always take away a vertex out of one
Excellent,
edge.
excellent, very good. Yes, that's the point I haven't addressed yet. That's excellent. Okay, so I remove that vertex X, and I'm happy. Everything will work out, right? So let's just write this. So G has k minus 1 plus 1 edges, and we're done. Okay, but yes, so what I didn't, so this is very nice in this picture, right? I just took out that nice little pendant vertex to say, but wait, is there always such a thing? And the answer is yes, there is always a pendant vertex, but I need to prove that, okay? Okay, so we need to make sure there exists such a vertex, pendant, or degree 1. Right? I used the fact that it had degree. If I had removed a vertex like in the middle of the tree, I would have broken this thing up into something that's not a tree anymore, and that would be bad. So I really need a vertex of degree 1 to be able to do this. So I'm going to prove, so I'm going to prove that every tree has a vertex of degree 1. And in the exercises, if you look at the exercises, there are very, very similar exercises to this one I'm going to do now, asking you to show various little things about trees and graphs and things like that. Okay, so fact or claim, every tree with at least 2 vertices has a vertex of degree 1. Okay. Does anybody see why this has, intuitively, why should this be true? So again, what is a tree? It is something which is connected and there are no cycles. Yeah. So if you're walking around in a graph like that, right? It's a finite graph. If you're walking around in a graph following edges like that, if you can always, whenever you reach a vertex, if every time you can go out again, at some point you'll have to cycle back. You can't go on forever. It's not an infinite graph, it's finite. But this is not possible. So it means that at some point you're going to reach a vertex where you can't go out anymore. And that's a vertex of degree 1. Okay, so let me write that. Okay, so otherwise, since the tree is connected, every vertex has degree at least 2, right? So you can't have vertices of degree 0, right? It's impossible. This thing is connected, so everybody has degree at least 1. If there's nobody of degree 1, then everybody has degree at least 2, right? So start in any vertex, let's say, yeah, and move to a neighbor, right? So you start, you choose a vertex, it has degree at least 2. So there's a neighbor, and then this one has another neighbor, and keep going, because everybody has degree at least 2. Once you go in, you can always go out, right? Keep going, but G is finite. So you must eventually return to some vertex you visited already. In other words, there exists a cycle, and that's a contradiction. Okay? So because a tree has no cycle and it is connected, if you start in a vertex and you start moving, following edges like that, eventually you must get stuck, because otherwise you'd have to loop back somewhere. Okay, that will create a cycle. Okay, so every tree has a vertex of degree 1. Okay, so I've told you my strategy, but there's still a lot of details that we have to check. You have to be careful, but that's the idea. That's once you have this idea, you're happy. So okay, I'm going to make it work. So I have a vertex of degree 1. I take it out and I look what's left. Okay, sorry. So look at what's left here. I said it's a tree with 1 less vertex. Why is it a tree? Because it's connected and because it has no cycle. But why is it connected? That's the only tricky part. The fact that it has no cycle is immediate. But okay, so back to our proof. What time is it? Okay. Back to our proof. Okay, so I have G, a tree with K plus 1 vertices. There exists an X vertex of degree 1. Let G prime be the subgraph of G induced by V remove X. Okay, so basically it's all the other vertices and the edges possibly between them. So essentially what it is that you take out X and the edge, the unique edge to X. Okay, just like in the picture I got earlier. Now, to use my induction hypothesis, I must make sure that G prime is a tree. So fact, G prime is a tree. Why is that? So what do I need to show? I need to show it doesn't contain a circuit and it is connected. So 1, it contains no circuit. Is this obvious? So G prime is in G. So if G prime had a circuit, so would G. It cannot. G is a tree, right? Since G prime is in G, a tree. So hopefully that part is clear. You can't have a circuit in G prime because it would be a circuit in G. The not so obvious part is it is connected. Okay, so let's go back to our picture. I've got X like that, and G prime is here. This, okay? I want to make sure that it is connected. So I take 2 vertices, W and Y. So take any two vertices W and Y in G prime. Okay, G is connected. That means that there exists a path, a walk from W to Y in G. Everybody agrees with it. This is the part where teaching remotely is 100% crap. Not that it's really good and usually, but this is really where I don't see anybody and I have no body language to see if you're following. It's really bad. Okay, so G is connected. So there is a path in G connecting W and Y. Everybody is okay with this?
Yeah.
Yeah, okay. Now, if this path is inside G prime, we are done, right? If this path does not use X, we are done, right? It means that I took arbitrary vertices in G prime and I found a path in G prime. So G prime is connected. So the only bad thing that could happen is that this path between W and Y uses X. Do you see that this is not a problem? Well, it could, right? So Rafael, so it could use X, but it doesn't need to, right? So which because it to go to X because it has degree 1, that was the whole point. It's that you'll have to go through that vertex that goes to X and come back. So you don't need to use it. Okay. So if uses X, we can remove it. Right? So let's say this goes like this because it'll have to go through this vertex here, right? So it goes like that, like this. It is useless. You don't need X. So you don't need X because forced to use its neighbor, right? So that's why G prime is connected. So if X did not have degree 1, we could this would not be true. Okay, so it is true that if you remove a vertex of degree 1 in a tree, what you get back is another tree. And so by induction hypothesis, G prime has k minus 1 edges. So G has k edges. And we're done. Okay, so that's the proof of the lemma. I haven't proved Euler's formula yet, but there's not that much work. I mean, just about the same that we just did. Okay, I will finish the proof of Euler's formula and I will stop after that. I'll keep the applications for Thursday. Okay, so now what have we shown? We've shown that any tree has always one less edge than it has vertices. Now I'd like to show Euler's formula. Okay, so now proof of Euler's formula. Euler did so much math, it's just nuts. He lived a long time and he wrote a lot of math in all sorts of different, I mean, he did physics, it's just like lots of stuff. Number theory, analysis, calculus, graph theory. I mean, it's just like, okay, here's the idea. Okay, so the idea for Euler's formula is also simple. Okay, here's the key. So it's induction. Induction on the number of edges this time. Okay. So what do I want to show? I want to show that V minus E plus F is equal to 2. So you take any planar connected graph, you count the vertices, edges, and faces, because it's planar, it has a planar representation, you count the faces. This should be true. I'm going to use induction number of edges. Now, we have seen, in fact, that the formula is true for trees. I haven't proved that trees are planar, but in any case, the formula holds for trees, okay? And the trick will be this. Take your planar representation, and suppose that if you have one less edge, you're good. So take out an edge, right? So here's the illustration. So here's the idea to illustrate this. So let's just draw a planar graph. Let's say like that, maybe like that. This is allowed, okay? So let's say I want to show that the formula is true for this graph and that it is true for graphs with one less edge. So what you do is, well, remove an edge in a face. So let's say I remove this edge, right? So you can see that you can control completely the number of vertices, edges, and faces that happens, right? So you're going to lose a face, you're going to lose an edge, but you're not going to lose any vertices, okay? So removing, let's write it in red. So removing an edge in a face will keep the same number of vertices, decrease the number of edges by 1, decrease the number of faces by 1, right? Because I'm opening up a face, two faces will be joined this way. Now, if you look at what happens like this, right, it's going to make the formula work because it works for the smaller graph. It has to work for the bigger graph. Okay, so that's the key observation. That's the key idea. Okay. So now what will we need? We need that when we remove an edge from a face, there has to be at least one closed face, right? And we have to make sure that what remains is a connected planar graph. Okay, so to make this work, we need at least one closed face. But if we don't, it's a tree and we're good, right? So that's why we did that case separately. And that the resulting graph after removal is planar and connected, right? Because if I want to use my induction hypothesis, I need a planar connected graph. The fact that it's planar is obvious because if I remove edges from a planar graph, I still get a planar graph. I'm not going to create crossings by removing edges. The difficulty, if there is one, is connectedness, but no, because there's cycles, so we'll be okay. So let's just do this properly, okay? So let's say I have, so the case where the number of edges is 1. Well, my graphs are simple graphs. They don't have any loops. So this is it, right? So V, E, and F, 2 vertices, 1 edge, 1 face. 2 minus 1 plus 1 is 2. So that it works, right? Okay, so now suppose the result is true for all planar connected graphs with k vertices, right? So this is my induction hypothesis that the formula is true for connected planar graphs with k vertices, and that, no, sorry. Edges. I'm doing induction on edges. Sorry about that. Okay, and now I'm going to take a planar connected graph with k plus 1 edges. Okay, so now let G be a connected planar graph with k plus 1 edges to show v minus e plus f is equal to 2, right? Where v is the number of vertices of G, e is the number of edges of G, which is k plus 1, and f is number of faces in a planar representation. Okay, so is that okay? I know I'm almost done. It's like there's 5 minutes left, so bear with me. Put away the booze. Yeah. Looks like a.
Yep.
Yep. Okay.
I think
I
my
see.
mic cut off.
I see a little thumbs up there. That's good. I feel less alone. Good. Yeah. Okay. So again, what I want to do is to remove, just as I'm asking this, I see people leaving. I see somebody left. Oh my God. So I want to take out an edge in a face. But if there's no closed face, what happens? Well, I have a tree, right? So case 1, G is a tree. Okay. But then we know that it works, right? So then V minus E plus F is equal to V minus 1 plus 1, which is 2. Right? If it's a tree, there's only one face. We did this argument earlier, and we have proved that the number of edges is 1 less than the number of vertices by the lemma, right? Okay, so if G is a tree, we're done. Case 2. G is not a tree. Yeah, I'm smart. Okay, so if G is not a tree, there is a circuit, which means there must be a closed face. So there exists a closed face. Does everybody believe this? I don't know if I need to go. If there is a circuit, there must be a closed face. Is that?
Yeah.
Yeah, okay. But just in case, because if you have a closed circuit like that, either there's nothing inside and it's a face itself, or there is stuff inside, so you can just look closer and closer and closer. You take a smallest possible circuit, you'll get a closed face. Okay. So
Wait, what do you?
Yep.
So what do you find? How do you define closed face?
Not the unbounded face.
Okay.
See it. Yeah, you nasty person. That's a good question. If we do it on a sphere, yeah, let's. What would be the proper way to define this? Okay, take a circuit, look at your planar representation. Take a circuit in the graph such that, I don't know how to do it without Jordan curve theorem. You really need to see this geometrically. There's no way to see it only as a combinatorial thing. You need to see the representation in the plane. So so I will define this as a region of the plane which is bounded by curves from the representation, which contains no point of the representation. Is this satisfying?
Okay, so there's no points within a closed
Correct.
space.
Yes,
Okay,
exactly.
that's what I was.
Yes,
confused about.
That's the key thing, that there are no points of the representation inside this sequence of paths, curves is the word I was looking for. Yes. So there's something that looks like that. And inside this thing, I have to use the Jordan curve theorem. So I split the plane or sphere into two pieces. And in that piece there are no curves, no points from the representation. That's
Okay.
Yeah, this is not, that's the unclean part of all of this stuff, which is me, myself, as a discrete math person. This is not the part that I really like, but it's really difficult to avoid. Okay, so G is not a tree. There's a closed face. Remove an edge from this face. Let's say yeah, okay, let's say this. Okay, so we obtain a new graph G prime with K edges. Okay, we're almost done. The only thing that I need is to make sure that this new graph is planar and connected. So G prime is clearly planar, right? I started with a planar representation and I removed something, so I can't create a crossing. It has to remain planar, right? It is connected. Why is that? Take two vertices in G prime, which is the same vertices as G. I didn't change the set of vertices. So I know G is connected, so there is a path in G connecting my two vertices. The only bad situation is if this path used that edge. But you see that I can, because it's in a closed face, if it used that edge, I can just, rather than use it, just go around the face on the other side, okay? So this is the argument, okay? So take X and Y vertices of G prime, then there exists a path in G from X to Y, okay? If it does not use the removed edge, we're happy. If it does, replace by edges in the face remaining. let me draw this. So you have the edge like that, and you have these things like that. Let's say X is here, Y is here, and there's a path that uses the edge that was removed. Well, rather than use that edge, just go around the face the other side. So you can still connect X and Y, even though you remove the edge. Is everybody okay with that?
Yep.
Yeah.
Yes. Okay, good. So G prime is connected and planar and has one less edge. So by induction hypothesis, Euler's formula is okay for G prime. So by induction hypothesis, Euler is true for G prime. Okay, so let's look at the parameters. So number of vertices of G prime is the number of vertices of G. I didn't change. Number of vertices, no, yes. Number of edges of G prime is the number of edges of G minus 1. And the number of faces of G prime is the number of faces of G minus 1. I've created an extra face. I've lost a face because I've opened it up. I removed an edge, so I've lost a face. That's an interesting way of saying. Okay, so if Euler's formula is true for G prime, it means that this minus that plus that is equal to 2, right? And so if this is true, then it has to be true for G also, right? So let's write it this way. V minus K plus F equals to 2. All right, sorry. Let's not, no, not like that. Okay, so let's say, let's call, so let V be the number of vertices in both. K is the number of edges in G prime. So K plus 1 is the number of edges in G, and let F be the number of faces in G. Okay, so what do we have? We have that V minus K plus 1 plus F. I'd like to make sure this is equal to 2, right? I want this to be 2. What is that? This is V minus K plus F minus 1, right? This is the number of vertices of G prime. This is the number of edges of G prime. This is the number of faces of G prime. So this is 2. And that's the proof. Yes. Okay, so yeah, there's a lot of little things that happened. There's a lot of couple of inductions, a lemma, there's a lot of stuff that happened, okay? But if you take a step back and look at the whole structure, it's not so bad, okay? So what we proved is, so recap, planar graphs are those that can be drawn on a sphere or in the plane without any crossings. Some graphs are planar, some graphs are not. We've seen an example of a non-planar graph, K33. We will see more on Thursday. There is a formula which is true for all planar graphs. So V minus E plus F equals to 2. How did we prove that? We proved it by induction. It's a trick by removing an edge. And to do that properly, we had to know that it was true for trees. So we looked at the case of trees separately. And to prove the case of trees, we had to use that little fact that the number of edges in a tree is 1 less than the number of vertices, which is a very useful fact. Okay, so that was the lecture today. Any questions, comments? Apparently not. Okay, so that's it for today. And I will continue Thursday with a few little applications of this. And we're almost there. Almost there.
Thank you.
See you.
Thank you.
Thank you.
Bye.
Bye.
Bye.